Hello viewers, welcome to this online lecture series of Internal Combustion Engine. I am Professor Digvijay Ronge. We are going to study now the chapter Engine Testing and Performance Enhancement. Now, for the sake of the simplicity, I have divided this chapter into three parts. The first part is power and efficiencies involved in engine. The second part, heat balance sheet and its numericals. Third part, performance enhancement, which involves supercharging and turbocharging. Now let's get started. Okay, so when a company decides to go for manufacturing of engine, it starts with a design. This design is backed by the theories, standards, and other norms. Then, prototype or a scale model is created. This prototype is tested. So, various companies are having their testing labs where this engine is tested based on various performance parameters. If this design is found to be okay, then it goes for mass level manufacturing. Then, if this tested model is not found okay, so not okay, then this is again sent back to the design where changes are being made and the process continues. So when I talk about performance parameters, these are broadly studied as first one power, second one efficiencies, third one fuel consumption. So this power, so mainly we are going to study indicated power, second brake power, and third friction power. Now on the efficiencies, we have various efficiencies. First one is indicated thermal. Second, we have brake thermal. Third, we have mechanical. Fourth, we have volumetric. Then we have relative efficiency. Sixth, we have scavenging. Seven, we have charge. And eight, we have combustion efficiency. So all these efficiencies are studied. Based on that, the performance of engine is being tested. Under fuel consumption, we'll study the fuel economy. So there are some parameters. So first one is indicated specific fuel consumption, and second one is brake specific fuel consumption or SFC. Now next we'll study the first parameter, that is power. Now we are very familiar with this figure. This is a SI engine. So we have an inlet port from where the air fuel mixture comes in. It has been ignited, combustion takes place inside the combustion chamber, and then the fuel gases or burnt gases, exhaust gases are being taken out. Now, when I talk about power, so what basically happens in a IC engine? Let's take a datum, zero energy datum. So, let's say this is the chemical energy with which fuel comes inside, and now that fuel burns, this chemical energy is being liberated inside the combustion chamber. So when that chemical energy is liberated, it again reduces to a level. So this level we call it as indicated power. Basically, this is a energy received by the piston during the combustion. Why there is so gap in between or difference between chemical energy and indicated power? This is due to radiation plus loss to the coolant and plus loss to exhaust gases. Because of this loss, we get a difference between chemical energy and indicated power. Now again, so this energy is being liberated here, that is your chemical energy. Whatever piston receives, that is your indicated power. Now we see there are some mating parts. So this is a one mating part, this is another mating part, this is another mating part. So friction takes place between mating parts. And due to that, whatever output we get, so output means crankshaft. So that output we call it as brake power. So due to friction, this power reduces, and we what we get as output, that is your brake power. And this difference is due to the friction plus pumping losses plus some unaccounted losses which we cannot measure. And finally, we get a brake power. So we start with the chemical energy liberated by fuel. Then we will get the indicated power, power received by the piston. And then finally we get at the crankshaft, that is your brake power. So from figure, can I say that integrated power minus brake power, that will give you frictional power. Next, we'll see what is meant by integrated power and what is a mean effective pressure. Now what you see on the screen, so this is your Otto cycle. In Otto cycle, the suction takes place inside a cylinder. So air fuel mixture comes inside. Piston is at PDC. Now the piston moves from BDC to the TDC. The compression takes place. At 2, the spark plug ignites the mixture and the combustion takes place. So 2 to 3 is your constant volume heat addition process. From 3 to 4 is your expansion or power store. At 4, piston is at BDC, and 4 to 1 is your constant volume heat rejection process. Now, whatever area inside this cycle 1, 2, 3, 4, so this area shown by the hatching lines is nothing but your indicated net work. So work done during this cycle, the area hatch, this is your indicated net work. Instead of the cycle, now what we have done here is we have drawn a rectangle, so its limits are fixed from BDC to the TDC. There is a rectangle A, B, C, D, and the area of this rectangle is equal to the area enclosed inside this Otto cycle. So what is here it is, so area of 1, 2, 3, 4 is equal to area inside A, B, C, D. So when these areas are equal, the pressure difference between point D and point A, the pressure at point D minus pressure at point A, point D pressure will be this, and the point A pressure will be this. These two pressures. So this pressure difference, what we call it as mean effective pressure. Now when this mean effective pressure is based on indicated power, we refer it as indicated mean effective pressure, or in other terms PIM. When this mean effective pressure is measured, the measurement is based on brake power. So in this figure this measurement is based on indicated power, but if it is based on brake power, it is called as brake mean effective pressure, or in other terms PBM. So first thing, if I measure indicated power based on indicated mean effective pressure, so this indicated power will be equal to mean effective pressure based on indicated power, that is PIM, into the piston displacement or the swept volume. This is written as equal to PIM into swept volume into small n into capital K divided by 60,000 kilowatt. So whatever you observe here, this is a per cycle. So this formula gives you indicated power in terms of kilowatt. Now here, swept volume, as we know, this is a product of stroke into area of the bore. The small n is equal to speed in RPM divided by 2 in case of 4-stroke engines, and this is equal to n in case of 2-stroke engines. This capital K is nothing but number of cylinders. From this formula you will get indicated power. Next we'll see the formula for brake power based on PBM. So second, the brake power based on brake mean effective pressure, that will be PBM into again swept volume into small n into capital K divided by 60,000 kilowatt. So here it was indicated mean effective pressure, here it is brake mean effective pressure. So if I calculate the mechanical efficiency, so that will be again brake power, that is the output, divided by indicated power. So this gives the idea what is a mean effective pressure and what is the indicated power based on indicated mean effective pressure, and what is the brake power based on brake mean effective pressure, and what is the mechanical efficiency. Next, we'll see different efficiencies involved in IC engines. So as per now, we have seen different powers, that is integrated power, friction power, and brake power, then mean effective pressure. Now we'll see what are the different efficiencies we defined in case of IC engines. So before that, we'll see first fuel power. What it is, this is actually a amount of heat liberated during combustion. So this is if I give it as a heat addition at constant volume, that is QH is equal to, that will be equal to mass flow rate of fuel into its calorific value. The calorific value, as we know, it is measured as kilojoule per kg of the fuel. So first efficiency, as we'll see, that is indicated thermal efficiency. So indicated thermal efficiency is the ratio of indicated power to the fuel power. It is the ratio of indicated power to the fuel power, which we give as mass flow rate of fuel into calorific value of the fuel. Next efficiency is brake thermal efficiency. This brake thermal efficiency is ratio of brake power to the fuel power. What is the ratio of brake power to the fuel power? That is nothing but product of mass flow rate of fuel into its calorific value. Next we have the C part is mechanical efficiency. So mechanical efficiency is the ratio, as we have seen, is the ratio of brake power to the indicated power. Brake power to the indicated power equals to brake mean effective pressure divided by indicated mean effective pressure. So that is PPM divided by PIM. Next, we have volumetric efficiency. Volumetric efficiency, as we know, it is the ratio of actual volume inducted inside the combustion chamber to the its swept volume. So this is the actual charge inducted divided by swept volume. This is equal to VA divided by Vs. Next we have relative efficiency. Relative efficiency. So relative efficiency, as its name suggests, it relates your actual efficiency to the maximum possible efficiency. So actual efficiency, that is nothing but your brake thermal efficiency to efficiency obtained from its air standard cycle. So this is your actual efficiency and this is your maximum efficiency. So likewise, we have other efficiencies, combustion efficiency, scavenging efficiency, charge efficiency. But keeping in point the numericals, we need this much formulas only. And some formulas related to fuel consumption. What are those? We'll see. So under engine performance parameters, we have seen power. Second, we have seen efficiency. Now third is fuel consumption. Now a vehicle, if I manufacture a vehicle which is having an engine which gives you maximum power, maximum efficiency, but it consumes a lot of fuel, will a normal customer will buy? No. So as Indians, we always look for better fuel economy. So how to measure that? For that we have a term which is called as specific fuel consumption. It is also termed as SFC. So this is nothing but amount of fuel consumed per unit power developed per hour. So this gives you grams of fuel per kilowatt of power per hour. So that is nothing but your specific fuel consumption. When this specific fuel consumption is based on brake power, we have a brake specific fuel consumption. Nothing but BSFC. This BSFC is the ratio of fuel consumed with gram per hour divided by brake power. So it is based on brake power. So we have a ratio of fuel consumed gram per hour divided by brake power. So this will give the unit as gram per kilowatt hour. Now second we have, as you might have guessed already, so there's nothing but indicated specific fuel consumption, ISFC. That ISFC will be again fuel consumed that is gram per hour divided by indicated power. Its unit will be again gram per kilowatt hour. So it should not be necessarily it should be gram. Sometimes it might be given in terms of kg. So we have studied three parameters. So first one was power. Second one was efficiency. And third, we have seen fuel consumption. So based on these formulas, we'll solve numericals in the next section. So let's start taking examples related to engine power and efficiencies. So first problem, find brake thermal efficiency of an engine which consumes 7 kg of fuel in 20 minutes and develops a brake power of 65 kilowatt. The calorific value of fuel used in the engine is 42,000. So what it is basically asking is to calculate a brake thermal efficiency. So the formula, so I'll just write given, what is the given data here. So given data here, it is mass which is given as 7 kg. The time T is given as 20 minutes. I will convert this time into seconds, so this will be 1200 seconds. Then the brake power is given as 65 kilowatt. The calorific value for the fuel is given as 42,000 kilojoule per kg. So whenever required, please take care of the unit. So if it is given in kilowatt, try to convert it into watt. If it is given in kilojoule, try to convert it into joule. Okay. So we'll start. So first thing, the formula for brake thermal efficiency, as we know, it is brake power divided by mass flow rate of fuel into calorific value. Now, first we'll calculate the mass flow rate of fuel. So mass flow rate of fuel can be calculated from the mass of fuel consumed divided by that time. So here it is mass is given as 7 kg and divided by the time, that is 1200 seconds. So this will give you the mass flow rate as 7 divided by 1200. So this will give you mass flow rate as 0.00583 kilogram per second. Now we have to just put these values into the formula for brake thermal efficiency. So that formula will take it again. Brake thermal efficiency will be equal to, now the brake power is given as 65 kilowatt divided by mass flow rate of fuel, which we just calculated, 0.00583, into the calorific value, which is given as 42,000. Now remember, the unit for this 65 is kilowatt. For 42,000, that is kilojoule per kg. If we are taking both in kilo, this is also in kilojoule, this is in kilowatt, then there is no need to go for into again watt and joule. Or if I convert this into watt, that will be 10 to power 3. This will be 10 to power 3. And these two will cancel ultimately. Okay. Now if I calculate this, I will get a value of 0.2653, or I'll say the brake thermal efficiency is 26.53. So this is how we calculate brake thermal efficiency based on brake power and the whatever heat liberated during the combustion. We'll take next problem. The next one, so it says an IC engine develops 36.8 kilowatt at full load. It requires 7.36 kilowatt to run the engine without fuel at the same speed. Find the mechanical efficiency in full load, 50% load and 25% load conditions. Now see, it has a sentence which says it requires 7.36 kilowatt to run the engine without the fuel at the same speed. So this refers to, so this sentence, it refers to the engine losses, or in general we'll call it as friction power. So if I write the given data, so the given in this problem, given is at full load, the brake power is given as 36.8 kilowatt and the friction power is given as 7.36 kilowatt. Now what is asked is there are three conditions. First is full load conditions, then 50% load is applied, and the third one is only 25% load is applied. In all these three conditions, we have to find out the mechanical efficiency. So we'll take the first case, A, that is the full load condition. Okay, the full load condition, brake power as given is 36.8 kilowatt. So the indicated power, as you know, is equal to brake power plus frictional power. So this will be again equal to 36.8 plus 7.36. So this will be 44.16 kilowatt. And the mechanical efficiency is given by the ratio, it is the ratio of brake power and indicated power. So this will be brake power divided by indicated power. So this will be equal to 36.8 divided by 44.16. So this gives you 0.833, or I'll say 83.3%. That is your first case, that is a full load condition. Now part B, is your 50% load applied, 50% load condition. So the brake power will be equal to 50%, that is the 0.5 of brake power applied at full load condition. So this will be equal to 18.4 kilowatt. Again, integrated power equal to brake power plus frictional power. This will equal to 18.4 plus 7.36. So this will be equal to 25.76 kilowatt. Again, the mechanical efficiency will be equal to brake power divided by indicated power. So in this case, it will be 18.4 divided by 25.76. So this will give you a value 0.7142 or efficiency 71.42%. So as you see, the load is decreased from full load to 50%. The efficiency also decreases. So it goes from 0.833 to 0.7142. Next we'll see the third case, that is 25% load. So in this case, brake power is 25% or 0.25 of brake power at full load condition. So this will be equal to 9.2 kilowatt. So indicated power, again it will be equal to brake power plus frictional power. So this will be equal to 9.2 plus 7.36. So this will be 16.56 kilowatt. Now we'll calculate the mechanical efficiency equal to brake power divided by integrated power. So equal to 9.2 divided by 16.56. So this is equal to 0.555 or 55.5% efficiency. Again, that efficiency decreases from 0.7142 to 0.555. So these were the three cases: full load condition, 50% load, and 25% load. Next problem is related to the specific fuel consumption. We'll see. So it says an IC engine producing 3.68 kilowatt of brake power is used for water pumping. Its indicated thermal efficiency is 0.3, mechanical efficiency is 0.8, calorific value of fuel is 42,000 kilojoule per kg, and specific gravity is 0.875. Find indicated specific fuel consumption, that is ISFC, and P brake specific fuel consumption, that is BSFC. So I'll just write down whatever given in this case. So the given this case, so brake power is given as 3.68 kilowatt. Then indicated thermal efficiency is given, that is 0.3. Then mechanical efficiency is given, that is 0.8. Calorific value of fuel is given, that is 42,000 kilojoule per kg. Specific gravity of fuel is given, that is 0.875. So from this I can calculate the density of fuel, which will be equal to 0.875 into density of water, that is 1000, equal to 875 kilogram per meter cube. Now we have to find out first is indicated specific fuel consumption and then brake specific fuel consumption. So I'll start the part A, that is ISFC. So we know the formula for ISFC, that is equal to fuel consumed, it is kilogram per hour, divided by indicated power. So here we'll first calculate indicated power, then we'll calculate the fuel consumed. So indicated power can be calculated from the mechanical efficiency, as mechanical efficiency is given and brake power is given. So mechanical efficiency is equal to brake power divided by indicated power. So it is given as 0.8 equal to 3.68 divided by indicated power. So this will give you the indicated power, that is equal to 3.68 divided by 0.8, so that will give you 4.6 kilowatt. Now next thing is to find out the mass flow rate, that is fuel consumed per hour. So I'll just continue this part here. So indicated thermal efficiency is given equal to indicated power divided by mass flow rate into calorific value. So this is the formula for indicated thermal efficiency. I'll write it the given value. So the indicated thermal efficiency is given as 0.3 equal to indicated power, just we calculated 4.6 divided by mass flow rate into calorific value 42,000 kilojoule per kilogram. So I have taken this is in kilojoule, this is in kilowatt, so no need to write again 10 to power 3. So again I'll calculate the mass flow rate from this. So this comes out to be 0.000365. So unit will be kilogram per second. Now if I want to calculate this is as kilogram per hour, so I have to multiply by 3600. So uh, per hour fuel consumption, that will be equal to again this 0.000365 into 3600. So this will give you 1.314 kilogram per hour. Now I can calculate ISFC easily. So ISFC is equal to fuel consumed per hour. So that is 1.314 divided by indicated power, that is 4.6 kilowatt. So this will be equal to 0.285. So unit will be kilogram per kilowatt hour. Similarly, I can calculate PS. So part B, that is PSFC. So that will be equal to fuel consumed divided by brake power. So this will be, I'll take the value 1.314 divided by brake power, that is given as 3.68. So the answer will be 0.357. Again the unit will be same, kilogram per kilowatt hour. So this is how we calculated ISFC and VSFC. Now we'll take the next problem. So it says a 6-cylinder gasoline engine operates on the four-stroke cycle. The bore of each cylinder is 80 mm and the stroke is 100 mm. The clearance volume per cylinder is 70 cc. At a speed of 4000 rpm, the fuel consumption is 20 gram per hour and the torque developed is 150 Newton meter. So calculate first is brake power, second brake mean effective pressure, C. Brake thermal efficiency. If the calorific value of the fuel is 43,000 kilojoule per kg, and D. The relative efficiency based on brake power, assuming the engine works on constant volume cycle. The gamma is given as 1.4. So I'll just start by noting down whatever given in this problem. So given. So this is basically a 6-cylinder 4-stroke engine. The diameter of bore is given as 80 mm. This is 0.08 meter. Stroke length is given as 100 mm. So that is 0.1 meter. Again, next is given clearance volume, that is VC. It is given as 70 cc. So you can convert this into meter cube as 70 into 10 to power minus 6 meter cube. Next is speed is given rpm, that n is equal to 4000 rpm. Fuel consumption is given, that is mf is equal to 20 kilogram per hour. So this I can convert into 20 divided by 3600 to convert into kilogram per second. So this will be equal to 0.0055 kilogram per second. Now next is given torque. Torque is given as 150 Newton meter, and then we have to calculate first is brake power, then brake mean effective pressure, then third is brake thermal efficiency. The calorific value of the fuel, that is given as CV equal to 43,000 kilojoule per kg, and the relative efficiency when the gamma is given here, gamma is given as 1.4. So we'll start with the first bit. So first A is your brake power. Now for a rotary motion, we know that P or brake power is given as 2 pi n t divided by 60. If it is a linear motion, then the power is a product of force and velocity. For a rotary motion, we have this formula 2 pi nt divided by 60. So I'll just put the values 2 pi 4000 into torque 150 divided by 60. So this will give you brake power as 62.83 kilowatt. So this is your first answer. So part B is brake mean effective pressure. What we note it as P suffix BM. So for that we have to use the formula of brake power is equal to PBM into Vs into small n into K, capital K, divided by 60,000. This will give you in kilowatt. So we'll first calculate each term. We'll start with the swept volume. So swept volume, as we know, is a formula is area into L. So this area is for a cylinder is for a circle. It is pi by 4 into t square. If I multiply this area with the stroke length L, that will give you swept volume. So I'll calculate this. Pi by 4 into D is 0.08 square into L is 0.1. So this will be equal to 0.0005 meter cube. Now second is n. So small n is equal to n by 2 in case of 4-stroke engines. So this is equal to 4000 divided by 2 equal to 2000 RPM. And K, it is 6 cylinder engine, so K will be equal to 6. I'll put all the values here. So 62.83 is equal to PBM into, that is 0.0005 into N is 2000 into 6 divided by 60,000. Sorry, 60,000. So if I calculate this, so this will be 62.83 equal to EBM into, I'll just calculate this part. So that will be 0.0001. So from this, the brake mean effective pressure can be calculated as 62.83 into 10 to power 4 pascals, or I can say 6.28 into 10 to power 5, that is nothing but bar. That is the answer for the second bit. Third is your brake thermal efficiency. So part C is brake thermal efficiency. So the formula for brake thermal efficiency is brake power divided by mass flow rate of fuel into calorific value. So this will be equal to brake power. We have calculated as 62.83 divided by mass flow rate of fuel, that is given as 0.0055 into calorific value is given as 43,000. So this gives brake thermal efficiency as 0.2656, nothing but can write it as 26.56% is your brake thermal efficiency. We'll move to the last point, that is the calculation of relative efficiency. So the last part is relative efficiency. Relative efficiency, formula for relative efficiency is actual efficiency or brake efficiency divided by maximum efficiency or efficiency obtained from air standard cycle. Now from previous bit we have calculated brake thermal efficiency as 0.2656. Air standard efficiency in this case, so as this engine operates on constant volume cycle, that is nothing but Otto cycle, so this will be efficiency for a Otto cycle. Now efficiency for Otto cycle, that formula is given by 1 minus 1 divided by R raised to gamma minus 1, where this R is your compression ratio, which is the ratio of total volume V divided by clearance volume. Total volume means clearance volume plus swept volume divided by Vc. So this will be equal to, clearance volume is given as 70 cc, that is nothing but 70 into 10 to power minus 6 meter cube, plus Vs we have calculated it as 0.0005 divided by again 70.24 minus 6. So when I calculate this, I'll get a compression ratio 8.14, which is very relevant for a petrol or gasoline engine. Compression ratio for petrol or SI engine is less compared to CI engine. Now I'll calculate the efficiency, Otto cycle efficiency, that will equal to 1 minus 1 divided by 8.14 raised to 1.4, gamma is given as 1.4 minus 1. Now I'll calculate this. So the value for this it comes out to be 0.5677. So efficiency is 56.77 for an air standard cycle. Next, if I calculate the relative efficiency now, that will come out to be relative efficiency equal to, so brake thermal efficiency is 0.2656 divided by 0.5677. So this comes out to be 0.4678, or it is 46.78%. As you see, we have calculated the relative efficiency. Here, the Otto cycle efficiency comes out to be 0.5677. Brake thermal efficiency is 0.2656, which is less than the Otto cycle efficiency. Why it is less? Because in air standard cycle, so in an air standard cycle, the working medium is ideal gas, and lots of assumptions are being made, like the walls are isothermal and the expansion is isentropic. But in actual cycle, it is based on fuel air cycle. So the working medium is fuel plus air, and some losses are considered. So losses may be time losses, exhaust blowdown losses, pumping losses, and other losses. Losses are considered. So that's why there is a difference between the efficiencies. For now, we have solved the numericals based on power and efficiencies. So this this part 1 ends. In next part, we'll see how to draw a heat balance sheet for a IC engine and the types of engine testing. Thanks for watching.